Have you ever wondered how to efficiently invert a matrix in Python? If you're dealing with large, symmetric, positive, definite matrices, you're in the right place. Today, we're diving into the world of NumPy and Cholesky decomposition to find out how to do this efficiently. I totally get it. Inverting matrices can be a real headache, especially when you're working with big data sets. You're not alone in this struggle. Many people face the same challenge when trying to optimize their calculations. Let's look at the specific question at hand. One user asked, which method is more efficient for inverting a symmetric positive definite matrix using NumPy's in function or Cholesky decomposition? This is a great question, and it's one that many data scientists and engineers grapple with. To understand this, we need to know a bit about how these methods work. The NumPy in function uses a general algorithm for matrix inversion, which can be computationally expensive for large matrices. On the other hand, Cholesky decomposition is specifically designed for symmetric positive definite matrices and can be much faster. And stick around. At the end of this video, I'll share a quick tip on how to choose the right method for your specific needs, which could save you a lot of time. To begin, the user should understand the two methods for matrix inversion. The first method uses the standard NumPy function, while the second method employs Cholesky decomposition. Let's explore how each method works. The user can see that the first method, which is the simple inversion, is executed with the command numpy.linealg.inv of the matrix X. This method is straightforward but can be computationally expensive for large matrices. In contrast, the second method involves first calculating the Cholesky decomposition of the matrix X. This is done using numpy.linealg.cholesky. The user then inverts the resulting lower triangular matrix and multiplies it by its transpose to obtain the inverse. Now let's compare the efficiency of both methods. The Cholesky decomposition method is generally faster because it reduces the number of calculations needed to find the inverse of a matrix, especially for large matrices. Finally, the user may wonder why numpy.linealg.inv does not use Cholesky decomposition internally. The reason is that NumPy aims to provide a general-purpose function that works for all types of matrices, not just symmetric positive definite ones. Fun fact, the Cholesky decomposition is named after the French mathematician André-Louis Cholesky, who introduced it in the early 20th century. Who knew math could have such a rich history? Now, let's look at the answers provided by other users. In this alternative approach, the user sets up a symmetric positive definite matrix using NumPy. They then compare the performance of two methods for matrix inversion. The first method uses np.linealg.inv directly, while the second method employs Cholesky decomposition followed by matrix multiplication. The user reports that the direct inversion takes about 255 microseconds, while the Cholesky method takes around 414 microseconds. This suggests that while Cholesky decomposition is theoretically more efficient for large matrices, in this specific case, the direct inversion was faster. Here's the tip I promised. When working with symmetric positive definite matrices, always consider using Cholesky decomposition for inversion. It can save you time and computational resources. And there you have it. You now know how to efficiently invert matrices using NumPy and Cholesky decomposition. If you found this video helpful, please subscribe for more tips and tricks on optimizing your data science workflows.